Okay, so next up we have Isaac Friend talking about identifying classical and quantum Markovian causal models from generalized observations.
Okay, thanks. So yeah, I'm going to deal with both classical and quantum causal inference problems at the same time. And I have to apologize that there's going to be some imprecision about the categories in which things are happening, but that is necessary to actually give all the ideas, and we can talk in more detail afterward. And some people may be able to actually tell, depending on your background. And I also have to thank Rob Speckens and Ellie Wolf of the Perimeter Institute in Ontario for drawing my attention to certain things associated with this topic, the ramifications of which are still being worked out. So I'm going to talk about causal identification, and I'll review what that means. And I'm going to also summarize how applied category theory people have dealt with causal identification in the past, and why their initial formulation posed difficulties for generalizing to cases of quantum causal inference. And then I'll show how we have gradually, over both past work and the present work, gotten over those problems. And we can also talk later about why people want to do quantum causal inference, but I won't go into the motivation right now. So a classical instance of causal identification means that one is given an observed joint distribution of a collection of random variables, and one is assuming that that distribution is being generated by causal mechanisms arranged in a network configuration, often depicted by a directed acyclic graph. And you know that graph. And the task is to determine how the data generating process, the unknown data generating process, would respond to interventions, where, for example, you would forcibly set a variable to a particular value while leaving everything else as it is in the rest of the process. Right, that's the causal identification problem for ordinary classical probabilistic situations. Now, the first attempt at a categorical formulation of this thing was given by Jacobs, Kissinger, and Zanasi. And the essence of their approach, which is maintained in what I'm going to be talking about, is to distinguish between the causal syntax, which is going to be given by a formal diagram in some sort of free process category, and particular models of the syntax, particular data generating processes, particular compositions of stochastic maps, which will be given by functorial interpretation of these formal diagrams into a concrete process theory of interest. So they were doing Finstoke. So here you have a traditional causal diagram that encodes causal assumptions about where there are independent mechanisms operating, and these nodes correspond to random variables. And then this is how they translate that into a formal string diagram. And the diagram, again, encodes qualitative assumptions about how the unknown data generating process is built out of those mechanisms that correspond to the boxes. And interpreting in some concrete copy discard category gives you a probability distribution generated by particular probabilistic maps arranged in this configuration. So there are many models of this one formal diagram, and causal identification means being confronted with an unknown model of the diagram and computing properties of the model such as the values of the boxes, the values of those actual channels, just from the observed distribution and the knowledge that the process decomposes according to the diagram. If you figure out the values of those boxes, then you can say what distribution would result from cutting wires and inserting fixed states independent of what's going on in the rest of the process. So that would mean you'd be able to identify the effects of hypothetical interventions. From now on, after this slide, all diagrams are going to be read in both a category of matrices containing stochastic maps and a category of linear maps between Hilbert spaces that's going to contain, among other things, quantum channels. And I won't say in what category the calculations are happening because the same diagrammatic rules are going to allow us to deal with both quantum and classical inference uniformly. But I want to note two things about this initial classical formulation that are going to create obstacles to the quantum generalization. The first is that we're assuming here perfect passive observational probing, and that is depicted by the fact that these variable values are being copied all the way up to the top as outputs. These are the things that you're going to see, that the observer is going to see. So they're being copied, and those same values are also being used as inputs to the rest of the data generating process. So in quantum theory, things are not going to work like that. Things, yeah, you won't have that. And that's related to the fact that quantum theory doesn't have any copy maps. And I want to emphasize that the copy maps here are also playing another role in addition to giving you the values of variables that are also being used in the future of the process. The copy maps are actually capturing assumptions about completeness of common causes. So we have been hearing all about conditional independence. And the idea is that these, for example, this fork originating from A means that whatever model you have, it has to be of this form where the value of A is simply copied and then used as input to two other independent stochastic maps. And so again, the quantum no cloning theorem means that we don't know initially how to make sense of a complete common cause assumption in a quantum setting. To summarize or to reiterate, the limitations are the perfect passive observational probing and the absence of the copy maps, meaning we don't really know what complete common cause and conditional independence mean. So the first way in which one can try to address these difficulties is by going to a more flexible kind of causal model that maintains the idea that you're going to have a formal diagram and then its interpretation into both quantum and classical process categories. So the diagram becomes a so-called comb, which maps first-order processes to probabilities. So the idea is that these gaps in wires are loci of intervention, where somebody could choose a way to probe the system or could choose an intervention to do, and the data generating process would respond. So it would tell you probabilities of outcomes of whatever probing schemes you might choose. And then we just don't try to represent complete common cause assumptions explicitly. There are aspects of the so-called causal Markov assumption that can be that are captured in this kind of diagram without any copy maps, and the resulting more generic notion of causal model is good enough for identification in latent variable scenarios in both classical and quantum settings. So again, you're going to be given this diagram, and you're going to be given the statistics from your particular causal scenario for a restricted class of probing schemes. And the question is, can you figure out the actual value of the overall data generating process? And for this particular diagram shape on the left, you can't, but what we showed was that you could get general versions of the so-called front door and back door criteria for causal identifiability in the quantum setting, as well as recovering the classical one. And for quantum observation, we will just say for the purposes of this talk that your restricted probing schemes that are allowed as observations will just be projective measurements. And we could talk about other ones later if somebody wants. Now we want to actually capture this idea that there is an assumption that a fork, two arrows coming out of an observed variable, means something very special about how the data generating process has to be constructed. So now we will actually go to a generic directed acyclic graph, and it will indicate an abstract causal structure as follows. Again, each vertex becomes an input-output pair that's going to be an intervention locus. And there are now two kinds of maps in the free process category where our formal string diagrams are drawn. There are processes feeding into each locus, and then there are the ones that have uppercase A's that come out of each locus. And a Markov assumption for a generic process category will be an assumption that those processes distributing the information, leaving a locus, to the various other processes that depend on it, in fact come from a certain subcategory of the concrete process category. And if that subcategory is sufficiently restrictive, then the Markov assumption may help with inference. And if not, then you won't be able to identify the model. So for instance, if we have a classical stochastic model of this diagram, where the A boxes can just be arbitrary stochastic maps, then this tells you nothing, and the power of the Markov assumption goes away entirely, and you can't identify the model just from the graph and from observational data. And similarly, quantum models where all the boxes, including the A's, can be just any quantum channels you like, won't be identifiable. But the idea in classical causal inference is that you're actually assuming that those boxes are deterministic functions. That is what ensures that there is no more correlation between descendants of a locus that is not explained by what happened at that locus. Yeah, and it's for this reason that if you're dealing with classical stochastic models and the distinguished subcategory where those A boxes have to be interpreted consists of deterministic maps, then you get to use this equation. And in the quantum case, it follows from work of John Mark Allen and others that unitary maps satisfy this kind of equation, where the black dots come from a non-commutative Dagger-Frobenius structure that is actually not in the category CPM of quantum maps, but it's in a category of linear maps between Hilbert spaces. And in particular, that thing taking over the role of the classical copy map is a quantum broadcasting map, which is not a physical process, but nonetheless, it can be used in calculations. So now we're going to see if we do have this knowledge that our common cause boxes, our A boxes, come from either process categories of unitaries or of functions on the classical side, then we can rewrite our formal diagrams in ways that will help us with inference. So I start with the given abstract causal structure on the left, the same one that we saw. And then if I know that the A's are going to satisfy that equation from the previous slide, I rewrite and I absorb the now two AX boxes into the unknown boxes Y and Z. So everything is still unknown, but I conclude that my unknown model has this form on the right. And even though the quantum reading of the dot doesn't actually copy, the Frobenius structures are enough to actually let us identify either a quantum model using our projective measurement statistics, or a classical model from passive observation via the same diagrammatic calculations. So again, the result is that for classical Markovian models of a graph where the common cause boxes are functions, we can identify the things from passive observational data. And similarly, for quantum Markovian models of one of those graphs where the boxes are unitary maps, the A boxes that come right after each locus are unitary maps, we can identify the data generating process just from projective measurement statistics. So quantum models, quantum Markovian causal models are identifiable from projective measurement is a summary of the new quantum result. But now, since we know now that it's not necessary to actually use, in the classical case, the fact that copy copies, since I said the same diagrammatic rules are used in both cases, and yeah, we just do not appeal to the concrete form of the classical copy maps, we can ask whether this lets us do any inference on the classical side that we didn't know how to do earlier. And the answer is yes. So you imagine a noisy kind of classical observation where what you're going to learn, you're going to have an instrument that lets you probe at some locus, and you're going to get some label on your instrument. And what this causes you to do is, since you know that your probing was imperfect, you're now going to ascribe a probability distribution to the possible values that variable might have had right before your interaction with it. So it's teaching you something probabilistic about what the values were, about what the value likely was coming into that locus, and that's going to propagate around and let you update your credences about other variables, but it's doing this still in a probabilistic way. And then you can also imagine that your probing scheme was disturbed the value of the variable. So you imagine that now the value of the variable that is fed forward from that locus after your probing is given by a probability distribution that is determined by your knowledge of how your instrument is likely to have disturbed the thing. Okay, so now we have noise everywhere, noise propagating backward for Bayesian updating, and noise propagating forward through the rest of the causal processes. And the point is, if you have just those very kind of imperfect instruments, can you identify classical Markovian models? So your observations are unsharp and they're disturbing, but they're unsharp and disturbing in ways that you have characterized. So you have characterized stochastically in a stochastic sense, you have characterized the behavior of your instruments. And the answer is that yes, you can, if you have enough of these kinds of instruments, then you will be able to do this kind of identification, even though you never get to actually see the values of variables. It's similar to hidden Markov models, where you're being, one of the things that you're given in an inference problem is those parameters that tell you the probabilities of observed states given hidden states. But this is slightly different because now you're also saying that you disturb the thing. So we're saying that you can identify Markovian causal models from generalized observations, which for Oxford people have outcomes of this form. We won't go into, we can go into this in more detail afterward. But the idea, or the point is that we recover from this quantum-inspired treatment both classical ordinary identification with perfect observations and new kinds of classical causal identification from noisy and disturbing observations. And yeah, I think probably after this, we will have to go through many of the details about what combs are again. So I'll try to leave plenty of time for that and just end with this summary. So models of this graph for which the common cause boxes are not assumed to come from a sufficiently restricted subtheory will not be identifiable. But if they do come from a sufficiently restricted subtheory, both in the quantum and the classical case, then they will be identifiable. And details about what these things, what these pairs mean, we can talk about. But now, yeah, I want to stop early and see if we need to circle around again, because there is a lot of stuff about quantum combs that people probably, a lot of people probably don't know about. So yeah, I'll stop there, and you tell me where in the early slides you want me to go back to and say things sort of again. I hope this will be the most helpful way to do it. Yeah. I'll leave that slide up there as well.
Thanks for the talk. You had this condition on this channel A with one input and two output, this basically conditional independence condition. And you mentioned that unitaries satisfy this, right? Do you know which other CPTP maps also satisfy this condition?
This is a special. So anything with noise is not.
So in the classical case, there will be.
Well, so unitary is followed by local noisy things. Outputs will, of course.
Right. Yeah.
But sorry, yeah, you were saying.
Yeah, I guess my question. I mean, this is a question that I'm interested in, but I don't know the answer to, which is, which CPTP maps precisely satisfy that condition?
Yeah, I don't think I think it will be. Certainly for isometries. Yeah. So and the isometries for which it is true will, I guess, be of that. The other systems involved in your isometry will be into your local things.
Thanks. Since you kind of asked for this one, why do people want to do quantum causal inference?
Because, so non-Markovian noise quantum information that affects correlated way creates problems. And then there is also now a newer literature that says a quantum network of some sort, they want to be able to tell whether there is and in causal inference language, that precisely means is there a we were not dealing with latent common cause. Markovian models are of more interest foundations people, but in quantum technology, they want to know how to detect whether there are those environments that are remembering stuff and keeping correlations over time that's affecting multiple interventions. Foundations, on the foundations side, quantum non-locality thought of as saying that you can't really get satisfactory common cause explanations for the outcomes of experiments and so people want to generalize framework of classical causal modeling to quantum causal models have complete quantum causes, but now you have redefined common cause to be this quantum thing, which is basically foundations people.
Great, very helpful, thanks.
Right, are there questions online?
Yes, I have a question.
Go for it.
Can I ask if you can use a different microphone? First of all, I'm sorry, the audio is a little bit dropping out sometimes.
Well, use this for now.
Oh. Okay, hello, can you hear me now?
Yeah, perfectly. So I don't know if you addressed this already, or my question is, do you know the work of Arthur Parzignat on quantum Markov categories, and if you have studied a little bit?
I have seen it, but not studied it.
Okay.
Yeah. It is on my list.
Yeah, because it's very, very related.
Okay, thank you.
Okay.